Okay, essentially we're going to move on to modules 21 and 22 together. Um, this might not be in the order that the modules go, but if you watch both of these lectures, both you'll see how those two modules fit together. So I'm going to start by talking about our first elimination reaction, the E2 reaction. Um, so in an SN2 reaction, we saw that our alkyl halide would react with a nucleophile. In this case, we're going to be reacting with something that acts as a base instead. So instead of our nucleophile directly attacking sigma star CBr, what our base is going to do is it's going to grab a hydrogen from next door. When it grabs that hydrogen, now the CH bond is going to break, and that's going to donate electrons into sigma star CBr, and that's going to break the CBr bond. What we end up doing then is making an alkene. Okay, this is like the reverse of addition of HBr to an alkene. Our donor-acceptor interactions here are that the lone pair on oxygen is donating to sigma star CH, while at the same time, sigma CH is donating to sigma star CBr. So we have the same ultimate acceptor as in an SN2 reaction, but it's happening indirectly. All right, thinking about stereochemistry, if I want to consider this sigma CH orbital, in order for this reaction to work, that sigma CH orbital is going to have to be overlapping with sigma star CBr. So sigma CH is here. It's donating into sigma star CBr. And at the same time, my oxygen lone pair, in this case, it's ethoxide. My oxygen lone pair is going to have to donate into sigma star CH. So I have oxygen lone pair donating to sigma star CH, while at the same time, sigma CH is donating to sigma star CBr. Notice that in order for this to work, I need sigma CH and sigma star CBr to be lined up with each other, which really means I need the hydrogen and the bromine to be across from each other. So this CH bond and the CBr bond need to have what we call an anti-relationship. They need to be directly across from each other. If I were to draw a Newman projection, looking from left to right here, my Newman projection, on the front carbon, I'd have hydrogen straight down, coming up and out of the page, I have the phenyl group. Up and into the page, I have a methyl group. And going straight up, I have the bromine. And coming down and to the right, I have the phenyl group. Going down and to the left, I have a hydrogen. So notice these two groups are directly across from each other. They have an anti-relationship. You might hear the term that we say they need to be across from each other and in the same plane. So they're often referred to as anti-periplanar. Periplanar just means in the same plane. So notice when I do this reaction, when I remove that hydrogen and that bromine and I flatten out the molecule, because in the end my alkene is planar, the two pH groups, the two phenyl groups in this case, will end up right next to each other. And then the methyl and the hydrogen will end up next to each other. So when I use this starting material, I will always make this product, which is in this case the Z product. If I started with a different stereochemistry in the starting material, then I could make the E product. But in this case, I'm only going to make the Z product. In terms of rate law, this is a single step and there are two molecules involved. So again, if you haven't covered kinetics before in your chemistry career, that's okay. You can ignore this part. But it would be rate equals K times the concentration of base times the concentration of my alkyl halide. So again, there are two molecules involved in that rate limiting step, which is where the 2 comes from. Okay, E2, the 2 means two molecules in the rate limiting step. In this case, it's actually the only step. But if there were subsequent steps in this mechanism, if this is the slow one, that's the one that matters for determining the rate law. So that's just where the name E2 comes from, if you're wondering why 2. Now, the thing is, in a lot of cases, you can have more than one possible isomer of the product. So, for instance, if I use, this would be 2-bromopentane as my starting material, and I react with a strong base, notice there are 3 different products I can get. Why are there 3 different products I could get? Well, I have some hydrogens on the end carbon here. All right. So if my base removes one of those hydrogens, I would make this green product. Okay. Then if I consider stereochemistry, let's say my bromine here was wedged coming out of the page. If I remove this dashed hydrogen on the neighboring carbon, then I would make this E product. If, on the other hand, I were to remove this purple hydrogen, then I would make this Z product. Okay. Now, why is that? Well, notice if I want to remove the purple hydrogen, right now it is not anti to the bromine. So before I could remove that purple hydrogen, I would need to rotate around the central bond so that the bromine is anti to the hydrogen that I'm removing. When I do that, what I would get is a situation where I have an ethyl group wedged. I could have my orange or my purple hydrogen be dashed. My orange hydrogen is now in the plane of the page. And I could keep the right side the same. So now my H and Br are anti to each other. So if I remove them right now, that's going to put the methyl group over here and the ethyl group on the same side of the molecule. And then I would have a hydrogen and a hydrogen. There's a hydrogen here on the same carbon as bromine. I would have a hydrogen and a hydrogen on the same. So that's why this would make that purple product, that Z product. So you do get a distribution of these products. You get mostly this anti-product with the alkene that's in the middle. That's generally going to be our major product. We like to give names to things after people. This product that makes the alkene with more substituents what we call the more substituted alkene is called the Zaitsev product. Uh, the purple one is also called the Zaitsev product because it does make a more substituted alkene. Now, between those two, generally the trans one or the E one will be a bit more stable because there's less of the two big groups bumping into each other. Um, so generally, we'll tend to make the Zaitsev product um, either mostly trans with some cis. Um, and then this green one over here, where I made the less substituted alkene, we call that the Hofmann product. So if you hear anyone talk about the Zaitsev elimination versus Hofmann elimination, Zaitsev basically means we made a more substituted alkene when given the choice. You also may notice 41 plus 14 is 55 plus 25. These only add up to 80%. So what do you think the other product might be? Well, I said an E2 reaction is when our other reactant acts as a base, but ethoxide can also act as a nucleophile. So my other potential mechanism would be if I had ethoxide act as a nucleophile and do an SN2 reaction. To make an ether. So note that that's a minor product in this case. We'll talk later about how we choose which of the two reactions to do, SN2 or E2. But for now, notice both can happen. So it turns out that what base you choose can affect which product you get more of, the Zaitsev or the Hofmann. So in this case, notice if I take this alkyl halide down at the bottom, when I react with ethoxide, I get 71% of the more substituted product. So 71% Zaitsev and only 29% Hofmann. So the Zaitsev is the major product. If, on the other hand, I use potassium tert-butoxide, so the difference between these is ethoxide is CH3, CH2, O minus. Tert-butoxide is a bigger, bulkier base. The fact that this is bigger and bulkier means that it's going to have a harder time getting to protons that are more on the interior of the molecule. It's going to have an easier time reaching the protons that are on the outside. So notice when I use the bulky base, I flip my percentages practically so that I get more Hofmann than Zaitsev. So the idea is use of a bulky base increases the likelihood of making the Hofmann product. And these percentages are going to vary depending on what substrate you're using. So the question always comes up, well, what do I do? How am I supposed to know what's going to be the major product, what's not going to be the major product? This is one of those gray areas of chemistry where If you were in the lab and you're doing a specific synthesis, you would have to try things out and try different bases to see what yields you got in each case. In the course that I teach, I've always tried to make some simplifying rules for students. So the rule that I have tended to give is that for any E2 reaction, if there are two products possible, the Zaitsev product and the Hofmann product, predict that the Zaitsev product will be the major product, even though that's not always true. So I give an example here where I could remove one of these hydrogens, or I could remove this hydrogen over here. And the question is, which one am I going to do? They'd give me two different products. So one would give me a Zaitsev product. The other one would give me a Hofmann product. And the question is, which is the major product? I want you to predict that the Zaitsev product is the major product. So make that prediction. It's not always going to be true, but just as a simplifying rule in your life. As long as you're taking chemistry with me, that's a prediction that is safe to make. If you find yourself in a situation where you need to choose the best base to make a specific product, if the product you want to make is more substituted, so if it's a Zaitsev product like this one down here, then choose a smaller base. So maybe methoxide or ethoxide would be a good choice. A smaller base to make that product. If you want to make the Hofmann product, then choose the big bulky base that will increase your chances of making that Hofmann product. So E2 is this elimination reaction. What we've seen so far is it has specific stereochemical requirement for the alignment of the sigma CH orbital and the sigma star CBr orbital. We've seen that sometimes it leads to a mix of products. And as a simplifying rule, I want you to assume you're going to make the more substituted alkene, so the alkene with more carbons coming off of it when possible, knowing that it's not always right. And if you use a bulky base, you're more likely to get more of the less substituted product. All right, so I've hinted at the idea that SN2 and E2 can both happen in the same situations. So how does one know which one is going to occur in a given situation? This is again one of those gray areas where I want to give you some guidelines for you to think about. So when you are given an alkyl halide and you're reacting with something that could be a base, could be a nucleophile, I want you to ask first about SN2, because usually SN2, where the nucleophile directly attacks sigma star CBr, usually that is the fastest reaction when possible. So if the leaving group is on a methyl carbon, then this is like just outstanding for SN2. So yay, SN2 all the way. If the leaving group is on a primary carbon, this is really good for SN2. So SN2 is going to be really fast. If the leaving group is on a secondary carbon, this is just okay for SN2. And remember, when the leaving group's on a tertiary carbon, this is terrible for SN2. Or really, it disqualifies SN2. So basically, there will be no SN2 in that case. One other factor to consider is ask yourself if that nucleophile or base, how big is it? If it's really bulky, that's kind of bad for SN2 because it makes it harder for that nucleophile to attack sigma star CBr. So the next factor you're going to consider is what kind of nucleophile do we have? Again, I've given you a list. So if you have one of those excellent nucleophiles, that's going to be great for SN2. If you have one of those good nucleophiles, that'll be good for SN2. But if your nucleophile is poor, then that would be unlikely to do an SN2. Okay, so that list of nucleophiles is going to be important to know. All right, so we've talked about SN2 so far. So I'd say evaluate whether SN2 is possible, how good it's going to be first, and then consider E2. So when you want to do E2, you need a strong base. So strong bases are going to have to be usually at least as strong as OH minus. That's great for E2. And what this means is the conjugate acid pKa will be greater than 15 or so. When we have bases that are between a pKa where the conjugate acid is between 0 and 15, that's just okay. And it makes E2 unlikely, but you might see it in some rare occasions. And then if the base is weaker than H2O, then definitely no E2 possible. All right, so given those factors to consider, let's look at some examples where both SN2 and E2 are possible. What I'd like you to do is pause, take a look at each of these examples, think about what you think the major reaction is going to be, SN2 or E2. Draw your product, and then once you're done with that, come back and watch the next part. Okay, the first thing I'm going to do for each of these is characterize my alkyl halide to start thinking about the sterics. So my first two are methyl halides, then I have primary halides, then I have a couple with secondary halides, and then I've got a tertiary halide. So that's my first step. So I'm already thinking methyl, great for SN2. Basically anything will do SN2 with a methyl. So then I look at my other reactant. I'm going to look at them at two things. Are they a good nucleophile and are they a strong base? So my first one, OH minus, is both a good nucleophile and a strong base. Okay. Since my substrate is methyl, sterics are good, SN2 is good, I'm going to say this is SN2 all the way. So my likely product is going to be just CH3OH. And then I minus is the byproduct. In my second case, I see that I have what is a bulky nucleophile. So not a great nucleophile. And it's also a strong base. Now, normally when I see this terbutoxide ion, I think, ooh, that's a bulky base. This is going to go E2. But notice, for E2 to happen, there needs to be at least two carbons because I need to be able to pull a hydrogen from a neighboring carbon. When I have a methyl alkyl halide, that's not even possible. So because in this case I have a methyl halide, the only thing I'm going to be able to do is SN2. And so my most likely product would be the SN2 product. So for the next one, my next three are primary halides. In each case, primary halides, I'm leaning towards SN2, as long as I have a good nucleophile, which I do in these first two cases. My first one, OH minus, is a good nucleophile and a strong base. So maybe there would be a little bit of E2, but I'm still thinking mostly SN2 in this case. So mostly I'd get the alcohol and then bromide as a byproduct. There might be a little bit of E2 mixed in. But that's going to be a minor product, so we're not going to worry about it so much. In the next one, I have CN minus, which is a good nucleophile and a weak base. So there, I'm not even worried about E2. That's going to be SN2 all the way. Now I have the third case with my primary substrate, and now I have a strong, bulky base. That's going to make it hard to do SN2. And in this case, unlike the methyl iodide above, in this case, there is a neighboring carbon that I can pull a hydrogen from. So E2 is a possibility. So I'm going to say E2 is my major product in this case. I would say I do get, as a byproduct, my terbutoxide will become terbutanol, but my substrate will turn into an alkene. All right, I'm going to skip the secondary cases because those are the gray area, the grayest areas. I'll go to the tertiary case. I know in a tertiary case, I can't have SN2. So as long as I have a strong base, I will do E2. So here I have OH minus, which is a good nucleophile, but also a strong base. Since my substrate is tertiary, I expect this to be mostly E2. All right, so the uh, the cases where my substrate is secondary, sorry, having a little trouble with the controls, trying to get this mark erased here. I'm going to pause, I'm going to close that and then open it up again. Okay, so with my secondary case, these sometimes get into really gray areas. In the case with OH minus, we said this is both a good nucleophile and a strong base, so both SN2 and E2 are possibilities. And its secondary, which I said is kind of okay for both of these. I'm marking this with a gray highlighter to say this is a very gray area. But what I want you to think about when you see this is, okay, E2 is usually going to win out. So I'm going to get mostly E2 with some SN2 mixed. It might be 60-40, it might be 70-30. I'll get mostly E2 and I'll get some SN2. The next case is not as gray because I have a good nucleophile that's also a weak base. So weak base means E2 is much less likely. So this is going to be mostly SN2. Oh, and it looks like I lost my notation down here from the tertiary case, so I'm just going to rewrite that. All right, so the bottom line is SN2 and E2 are in competition, and we have to do a bit of thinking in order to figure out what is the most likely reaction in any case. And we do run into some cases that are going to be gray areas. That covers pretty much module 22. From here, I'm going to go back and talk about the other two substitution elimination reactions we haven't mentioned yet, the SN1 and the E1. So if you're looking at module 21 about SN1, you're going to want to stay tuned for that.